So we have to, if we want to find this volume, we have to bound the y if we do dy dx. If we do dx dy, we have to first bound the x. But dy dx is probably the way that you would set up most integrals. Not all, but most. And so first you have to figure out, you have to look at your equation, set z equal to 0, and then solve for y so that you can bound the y. And when you solve for y, you get y equals plus or minus that radical there, and that's why they have the negative radical first, and then they have the positive one on the right side. So see here, the negative one and the positive one. That's what you get whenever you set z equal to 0 and you solve for y. And that's your lower and upper bounds on your integral. This right here, this is your function. That's your f of xy, or your z. So if you integrate this, and then you plug in the top minus plug in the bottom, you might want to practice that. When you integrate, remember you're integrating with respect to y, so you're plugging that in for y, and you end up getting just, you get some crazy constant here, but you end up getting just this. You might want to practice that because it does not happen very easily. Okay? Whenever you get this, then you have to recognize that this is one of the trig substitution integrals from chapter 8. So this is in the form, I believe it's a squared minus u squared to a power. And so you have to use the trig substitution, let x equal 2 sine theta to integrate this now. So they let x equal 2 sine theta, they plugged it in. And whenever you plug that in right here, you're going to have 4 minus 4 sine squared. All that's raised to the 3/2 power. So you have to factor a 4 out, but then your 4 is raised to the 3/2 power. That's where the 16 comes from. And you'll have 1 minus sine squared here. And 1 minus sine squared is the same as cosine squared. Cosine squared to the 3/2 power is cosine to the 4th. So the reason why we have cosine to the 4th is because of that power. Then you just continue to plug and chug and work out. But look at this. Originally, we were bound from -2 to 2 on the x. When we change this right here, our boundaries have to become, if we're using this trig substitution, now instead of numbers here, we have to plug in angle measures. So if you plug this 2 here into this formula right here, plug this in right here, then you'd have sine of theta equal 2 equals 2 sine theta, or sine theta equals 1. Sine of theta is equal to 1 at pi over 2. Then if you plug in this bottom number here, you're going to have -2 equals 2 sine theta. So you get sine theta equals -1. Now you may think 3 pi over 2, that's when sine is equal to -1. But they didn't put in 3 pi over 2 here because that wouldn't make sense. You can't integrate from 3 pi over 2 to pi over 2, right? If you have, if you're integrating from here to here, this is 3 pi over 2, but if you're integrating, you have to think about it as -pi over 2. And so integrating from there to there, from -pi over 2 to pi over 2. So that's why that changed to -pi over 2.
And then they use symmetry. It looks like they use symmetry. From here, they then just integrated from 0 to pi over 2 since this figure is symmetrical. Well, here's the actual figure. Since it's symmetrical, they're integrating from here to there. Or actually, 0 is going to be kind of hard to tell here. If this is the XY plane and this is the first quadrant, if you're looking at it in 2 dimensions, then they're going from here, from 0 to pi over 2, and they're actually just finding the volume of the first octant, and then they're saying that times 2. Okay.
Because they only want half of that shape.
No. We've already taken the other parts into account whenever we were integrating, when we integrated the first time. So that problem is actually very complicated because you have to do a lot of trig, a lot of integrals that may not be on your mind. Alright, this is a very good example because they integrate dy dx and dx dy. If it's dy dx, remember, first you have to bound the y. Well, it's already given to you up here, but y is between 0 and x. And then you bound the x, 0 to 1. If you set it up dx dy, then you have to bound the x first. And the way that they do that looks like they figure out the equation of this line. The equation of this line is going to be, I believe it's y equals, what would it be? Well, you could figure it out. It's not too hard to figure out. But especially if they give you the boundaries, those are really easy to set up. It's if you don't have the boundaries, whenever you have to do a lot of crazy stuff. Alright. So that's what we were working on last class period. Hopefully you can practice. Always try dy dx first unless the directions say otherwise. And let z equal 0, bound your y, find your upper and lower boundaries, then bound your x by letting z equal 0 and y equal 0 and solve them. Now 14.3 is probably one of the most confusing sections. I believe this is the one that is, whenever you start changing things around, it's because we really don't think in polar a lot. We think more in the rectangular coordinate system, and so if you change orders of integration with polar, it becomes a little more confusing. But that's what we're going to look at for a little bit today. We'll do about as much as your brain can take, I guess. No, it's not good. Alright. So, some of the things that we have to remember to deal in polar: x equals r cosine theta, y equals r sine theta, r squared equals x squared plus y squared, and tangent of theta equals y over x. Alright, and so if we have a double integral of some region in rectangular, then, and we change that over to polar, instead of x's and y's, we're going to have r's and thetas. But the formula we have to use, the double integral, it's going to be some function of theta as a lower bound to some function of some other function of theta as an upper bound for this inside integral. And then of course we have to change the function. It's going to have to be in terms of r cosine and r sine. And instead of dA, it's r dr d theta. So the differential dA that we let be dy dx in rectangular is r dr d theta in polar. And then, so if I first integrate with respect to r, you know, this is going to be some radius, this is going to be some radius, and then next I integrate with respect to theta. What were these boundaries have to be right here? If I'm integrating with respect to theta, they're going to have to be angle measures. And so this is from alpha to beta. Alright, so let's look at this example. Alright, let R be the angular region lying between two circles. So we have this circle, x squared plus y squared equals 1. What kind of circle is that?
Ellipsoid. No, it's not ellipsoid. That's not a circle.
Red triangle? That's the unit circle. If you didn't know what the unit circle was, you're missing out. The unit circle is awesome. And then, so that's going to be centered at 0, 0 and have a radius of 1. And here's your other circle, centered at 0, 0 and have a radius of square root of 5. So here to here is 1 unit. Here to here is the square root of 5 units. Alright, so if we wanted to find the double integral of this function about this region, then how would we set it up? So you have to change this function right here. You know, this function right here may be a density of this object, because that's one way that double and triple integrals can be. This right here doesn't necessarily have to be something with this. There's no z here, right? So this could actually be, you know, like I said, it could be the density of a piece of an object. And then we could find all kinds of different things, like maybe center of mass with different formulas, and moments of inertia and things like that. And so since I have to change this over to polar, so you simply put in r cosine theta for x and r sine theta for y. So if I put that in right here, you'd have to square it. Does everybody see that? That's why we have r squared cosine squared. Because if you plug in r cosine theta, you have to square it. Then we have r sine theta that we plug in for the y. Now this is important here. This is part of my differential, but it's also just a variable r. So you do have to take this r and multiply it in times both of those r's. Make yourself a note. That's very important. If you leave that r out, you're guaranteed to get the problem wrong. You know, that's part of the dA, that's part of our differential, but it's just a variable. And that's always there whenever you convert over to polar and do integrals. Alright, so you multiply that in, and then we have dr d theta. So the first differential here, this dr, that means that we need to use r values. We need to bound our r. And remember, we could tell that the radius is going to be what? Between 1, so here's a radius of 1, and the square root of 5. So you see the boundaries? 1 to the square root of 5. D theta, 0 to 2 pi. All the way around. If for some reason, if you work out a problem and you get an answer of 0, then you might want to use symmetry. The way that you're thinking about things may not be the way that you need to think about them. So you could, since this thing is symmetrical, you could say the angle measure, you could say between 0 and pi over 2 and say that answer times 4. Or you could say the integral from 0 to pi and then say that answer times 2. So you can always use symmetry if it's more convenient for you, or if it helps you understand the problem more, if the figure is symmetrical. And so here they integrated with respect to r. Remember, the thetas are constants, so you don't have to have du's there. They integrated with respect to r, and then they plugged in their values, and they got this right here. Then they integrated, or it looks like once they got this right here, they said, uh-oh, how do I integrate cosine squared? And so you can't integrate cosine squared unless you have a sign in front of it, or a negative sign in front of it. So what did they do to go from here to here? They applied the power reducing formula. Remember, when you integrate cosine squared of theta, the only way to integrate this is by first applying the trig identity. Alright, that's the integral of 1/2 times 1 plus cosine 2 theta d theta. That's the power reducing formula. That's what they did to go from here to here. Lastly, once they had this thing, this integrand in a form you can integrate, they took and they integrated the 3, they integrated the cosine, they integrated the sine, and now we're going to plug in 2 pi and work that out, and then subtract, plug in 0 and work that out. And after you do all of that, you may want to practice on this, you end up getting 6 pi. That's your volume. Alright, any questions? So you have to first convert from, and we haven't even switched the order of integration or anything, so this is as easy as these get about. So first you have to convert from rectangular to polar. Then remember to change your differential. the dA, that would be dy dx, changes to r dr d theta. If you leave the r off, you're guaranteed to miss the problem. Then you multiply your r in, bound your r and bound your theta, integrate your r, and you're going to have some trig stuff, so you have to rewrite things and deal with the trig. Then integrate the trig and evaluate at whatever you set your boundaries as. Alright, let's look at another example. Use polar coordinates to find the volume of the solid region bounded above by the hemisphere z equals the square root of 16 minus x squared minus y squared, and below by the circular region r. So this right here in 2 dimensions, this x squared plus y squared is less than or equal to 4, is that circular region down there. And so it has no z, so it would extend without bound both ways. But what we're trying to figure out is the volume that is created by bounding this hemisphere and putting this cylinder. Well, it's really a circle extended up infinitely. Okay. And so the first thing we have to do is figure out what would our integral be if we were talking about this in rectangular. So you can bound the x by moving the y over and taking the square root of both sides. You see they bound the x here. Well, if I let x equal 0, how do I bound my y? You take the square root of both sides. Y is between -2 and 2. Then look up here. The z is bound. This figure, it says the z is bound between 0 and the square root of 16 minus x squared minus y squared. That's the formula for that hemisphere. It's a square root. It's not a sphere because of the square root. If you square both sides and you move everything to one side, it becomes a sphere. Alright. And so let's see how we would set that up to find the volume. You can set it up in rectangular if you want. Look at this right here. This is that's probably what I would do first. That's my z, so that goes right here. And then you can either set it up dx dy or dy dx. Either way is fine. They set this up dx dy, that's why they first bound the x here. Alright, and so there are your boundaries, and then they bound the y by letting x equal 0. You could have done just the opposite. You could have worked this out dy dx and it would be very similar. Okay. Now, me personally, I then go from this right here, where they have the rectangular double integral here, I go from here to here. And the way you do that, if you were to take this right here and factor a negative out of those two terms, that becomes x squared plus y squared there under the radical. That's the same thing as r squared. Okay? So that's why they have 16 minus r squared. why is there an R out here? That's right. That's part of my differential, right? Usually we have dy dx or dx dy here for that. But remember, with polar, it's r dr d theta. Okay? How do we get these boundaries? Well, r is a radius, right? If I integrate with respect to r, then these have to be, that has to be radius. And what's the radius here? If you let, let's see, where are we? If you look at this equation here, the radius, 0 to 2, how do you get that? Well, think about this like x squared plus y squared equals 4. So the radius is 2. So you see 0 to 2. That's your radius. And then the angle measure all the way around. 0 to 2 pi. If this r wasn't out here, this integral becomes a lot more complicated. Because when you integrate, your u is equal to 16 minus r squared, so your du is equal to negative 2r. Alright, so you have to bring out a negative 1/2. Negative 1/2. And then when you integrate, that's going to be u to the 1/2. Because you have your du. This is right there. That's right there. Let's bring out your negative 1/2. Then when you integrate, you add 1 to the power, it becomes 3/2. Divide by that, so you multiply by 2/3. So that's why they have that negative 1/2 on the outside. And now they've integrated. This is the answer once you integrate with respect to r. And you have to plug in from 0 to 2. So they just have this big constant right here. That's, because you're plugging in numbers for r. And then they have d theta. So the integral of a constant d theta is theta. So when you integrate here, you get theta. And then you plug in 2 pi. And then you say minus, and you plug in 0. So really you're just plugging in 2 pi there. And when you plug in 2 pi, your answer that you get, really you can just say, let's see, plug in 2 pi. I'm just wondering, you shouldn't get a negative. So whatever if we just multiply the front by 2 pi, that will be negative 16 pi over 3 times 3 square roots of 3 minus 8. So this better be negative when you work it out. If it's not, then we're not going to get a positive answer. So let's just double check that real quick. 3 times 3 square root, alright, minus 8. So that times negative 16 pi, so times 16 negative times pi divided by 3. Alright, so that's your volume. About approximately 46.98 cubic units. Alright, so there's a lot that goes into this. You have to be careful. You need to be semi-good at setting it up in rectangular form, and then from rectangular form you can change that over to polar form. And that's basically what you have to do. Well, I close my book. I can remember when we went over this in Cal 3, some of you had some problems finding these radial lines, finding the equation of these radial lines. So you've got to be careful. If you set this up r dr d theta, your r, your radius, is going to depend on your function. You see they have from 0 to this right here. That's your radius. But to set up the thetas, that's the hard part. That's the hard part for most students, because you have to set 3 cosine 3 theta equal to 0 and solve, and you get those values, that negative pi over 6 to pi over 6. So let me show you that. So assuming that you can set up this first part, let's see what we have to do to get these boundaries. So if I take this 3 cosine 3 theta, I'm trying to figure out those radial lines. So we set that equal to 0. So it's cosine 3 theta equals 0. Cosine is equal to 0 at pi over 2 and 3 pi over 2. Here and here. But remember, if our figure looks like this, and it would be good to graph this in the graphing calculator to know what it looks like. If our figure looks like this, we have a lot of options. We can go from this radial line to this radial line, or we could go from 0 to this radial line and then just say the answer times what? Times 2. If I'm trying to figure out this, you could go from 0 to this radial line and say it times 2. But we still have to figure out that radial line. Alright, so the way that you do that, you write down the answer for theta. The cosine of theta is pi over 2, but we don't have theta, we have 3 theta. So to get the answer, divide both sides by 3. That's pi over 6. Alright, so that's how you know that this is theta equals pi over 6 in polar.
So you knew you wanted in those 2 quadrants to save it.
Yeah. It should, your answer should work out. Like if I was to work this out with 3 pi over 2, it's going to give me this down here, but it's going to give it to me as a positive angle measure. Like if I say 3 theta equals 3 pi over 2, so that's 3 pi over 6. See, it's giving it to me as a positive. So what you'd want to do, if you wanted to find this lower boundary and not use symmetry, you'd want to do the same thing we did here, but make that a negative pi over 2. And so your integral, you can go from negative pi over 6 to pi over 6, or you can say 2 times the integral from 0 to pi over 6. Either one of those will be okay. But that's going to be, you just put that constant out in front of your double integral. So here where you have a double integral, you just move that 2 in front here if you want to go from 0 to pi over 6. Either way, you get the same answer. Definitely going to have to practice on these if your trig is not up to speed.